few generic examples of how we can define a random variable. We talked about mapping the random variable to a particular event, and talking also now, given the probability of an event, we associated probability of the random variable taking a particular value. So now let's look at an application wherein we define a random variable and we get the probability of these random variables through the events they correspond to. The application is an application from life insurance. So I have a life insurance agent who has two elderly clients. Okay, both of them have a life insurance policy that pays 1 lakh upon death, rupees 1 lakh upon death. So this is a hypothetical case. I have two people and both of them have insured life insurance, and they will get a payout. That is, the people, the survivor, the nominees would get a payout of 1 lakh upon their death. So I am defining two events. Now what is a random experiment here? So the random experiment is, I want to know in the next year, okay, in the following year, what are the possible things that could happen? The possible things that could happen is both of them die in the following year, both of them die, or one of them die, or none of them die. These are the possible things that could happen in the following year. Now, when both of them die, I know both die, one of them dies. So, if I am calling A and B, A dies, B survives, or A survives and B dies, or both A and B survive. These are the possible outcomes if I am talking of this in terms of a random experiment. So now let A be the event that the younger one dies. Okay. So between the two of them, I assume one is older and one is younger. So I am calling A, I am letting A to be the event that the younger one dies the following year, and B to be the event that the older one dies in the following year. So I said, what are the outcome? The outcome is both die. So this corresponds to both event A and B happening. Younger one dies, older one survives, only A happens, B does not happen. Older one dies, only older one, only younger one dies, only older one dies. So here A does not happen, B happens, both survive, both A and B do not happen. I hope this is clear. So I have just first, these are the possible outcomes, and this I have listed or mapped each one of the possible outcomes to in terms of the event. When both die, I say both events A and B happens, and I know mathematically I can express this as A intersection B. Only the younger one dies, but the older one does not die. It is A intersection B complement. A does not die, A complement happens, but and B happens, A complement intersection B. Both A and B do not die, so A complement intersection B complement. So in terms of events, we can translate whatever we are expressing in plain English in the mathematical abstraction. Now, we want to associate. So now the next thing is, I assume A and B are independent. This is absolutely a very valid assumption, because when I am talking about two people dying, it need not be the case that one's death affects anybody. So the events are independent, and I am associating some subjective probabilities. Perhaps I am associating a probability A which is very low with the younger one, and probability B which is 0.1 with the older one. Now let X denote the total money that the company pays out in this year to its clients' beneficiaries in amount of lakhs. Okay. So what is the company note will pay out money only if there is a death. Let's assume that the company pays out the money only if there is a death. So X is the total amount of money that is paid out to any one of the client's beneficiaries. So again, let's go back to our earlier thing. I had both dying. So when both die, the company has to give money, okay. When both die, it gives money to both the beneficiaries. When the younger one dies, it gives, and both of them have insured for the same amount. So when both die, both of them have insured for 1 lakh upon death. So I will have to pay 2 lakhs to both the beneficiaries. Only the younger one dies, I pay 1 lakh to the younger one's family. Older one dies, I pay 1 lakh to the older one family. When both of them survive, I don't have to pay anything. So my payment is 0 lakhs. So if you look at the value this X is taking, it is taking the value 0, it is taking the value 1, and it is taking the value 2. I repeat, the value X is taking the value 0, X is taking the value 1, and X is taking the value 2. Okay. And you can see that X taking the value 2 is corresponding to the event that both of them die, which again corresponds to both A and B happening, which is written as A intersection B. Similarly, the value of 0 corresponds to both surviving, which is same as both A and B do not happen, which is probability of A intersection B complement. A complement intersection B complement. But you can see that the probability of X taking the value 1 can happen if only the younger one dies or only the older one dies. Only the younger one dies corresponds to A intersection B complement. Only the older one dies corresponds to A complement intersection B. So if one of these two events happen, I know X takes the value 1. We have already seen earlier, A or B happens is represented by A union B. Here I am not talking about A or B, I am talking about A intersection B complement or A complement intersection B for the value of X to be equal to 1. So we can summarize the discussion by saying that X takes the values. What are the values X takes? X takes the value 0. The relevant event is A complement intersection B complement. That is what we just established a couple of minutes before, that this A, X takes the value 0 is with A complement intersection B complement, takes the value 1 with A intersection B complement union A complement intersection B, and X takes the value 2 with probability of A intersection B. It is equivalent to A intersection B. So, X takes the value 0, relevant event is A complement intersection B complement. 1, it is A intersection B complement union A complement intersection B. It takes the value 2. These are the only 3 values X can take is A intersection B. Again, as in the previous case, I can associate probabilities to, I want to know what is the probability with which X does not give out any money. Probability with X gives out a payout of 1 lakh, probability with which X gives out a payout of 2 lakhs. See, these are the numerical values associated with the outcomes of the experiment. So, you can see that probability X equal to 0 is same as probability of A complement intersection B complement, which I know if A and B are independent, A complement is also independent of B complement, and we also know A intersection B is probability of A into probability of B. This is the multiplication rule. So, I have this is probability of A complement into probability of B complement. What is given to us is probability of A is 0.05, probability of B is 0.1, which gives us probability of A complement is 0.95 and probability of B complement is 0.9. Hence, I have probability of A complement is 0.95 into a 0.9. So, I have probability x takes the value 0 is 0.95 into 0.9, which is given by 0.855. Similarly, probability x equal to 1. Probability x equal to 1 is again probability of A intersection B complement union A complement intersection B. We can check that these two are disjoint sets, and we know for any two disjoint sets, probability of A union B is probability of A plus probability of B. This is my addition rule for disjoint sets. I can use that. I know probability x equal to 1 is probability of A intersection B complement union A complement intersection B, which is probability of A intersection B complement plus probability of A complement intersection B. Again, if A and B are independent, A is independent of B complement. So, this would be probability of A into probability of B complement plus probability of A complement into probability of B. Again, we know probability of A is 0.05, probability of B is 0.1. So, I have this as 0.05 into 0.1 plus 0.95 into 0.9 here, sorry, 0.9 here into 0.1. 0.05 into 0.9 plus 0.95 into 0.1, that is my probability x equal to 1, which is 0.05 into 0.9 plus 0.9 into 0.1, which is 0.140. Finally, I want to know what is probability x equal to 2. This is probability A intersection B. Again, A and B are independent. So, this is probability of A into probability of B. We know probability of A is 0.05, probability of B is 0.1. So, I can get the probability of A x equal to 2 is 0.005. Okay. So, what we have seen is, I have from given the events A and B and their respective probabilities, I am associating the relevant events to the values x can take to get what is the probability of x equal to 0, x equal to 1 and x equal to 2. So, this is a simple application of how we define a random variable and associate probabilities to that random variable. So, what is next? So, if you look at what we are going to do in the first portion of the next few weeks is we are going to look at discrete random variable. So, what is a discrete random variable? A discrete random variable can be formally defined as a random variable that can take on at most a countable number of possible values. In other words, we will look at examples where a random variable can take on a finite number of values. For example, x takes a value 0, 1, 2, 3, finite number of values, or x could take a value x 1, 2, 3, 4, so forth, countably infinite, but it has to be countable. You have already learnt about what is countable sets or what is properties of countability in your mathematics courses, but what I want you to understand is a random variable which can take on a finite number or a countably infinite number is referred to as a discrete random variable. Now, there could be random variables whose set of values are uncountable. Now, I am not going to formally define a continuous random variable, but then when the outcomes of a random variable are numerical but cannot be counted on and are infinitely divisible, we have continuous random variables. The formal definition of a continuous random variable is slightly more involved. I will come to it when we specifically look at the continuous random variable case, but for now we are going to focus on discrete random variables. So, in summary, what we have learned in this module is we introduce the extremely important concept of what is a random variable, namely a numerical quantity associated with outcomes of a sample space, and then through actually mapping it to relevant events from the sample space, we computed what was the probability of a random variable. This is what we did. Then we defined what are discrete and continuous random variables. We did not give a very rigorous definition of a continuous random variable, but whenever a random variable takes countable number of values, we typically refer to them as discrete. Otherwise, we refer to them as continuous random variables. So, moving forward, we would focus on a discrete random variable and how do we describe this discrete random variables in terms of its distribution is what is going to be of interest next.